Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 10, Lesson 5 on the zeros of a polynomial function. Okay, so we've been now studying polynomial functions, how they look, how they behave in the long run, how the zeros relate to their degree, how the number of turning points relate to their degree. Today we're going to play around with finding the zeros of polynomials algebraically, and we're also going to play around with how we can write the equation of the polynomial if we know what the zeros are. So let's jump right into it. Here we go. Zeros and polynomials. As we have seen already, the zeros of a polynomial function are related to both its factors and its degree. Let's take a look at that in exercise number 1. Given the polynomial function f of x equals x cubed minus 5x squared minus 9x plus 45, do the following. Letter A, write the polynomial in completely factored form. Awesome. So what I want you to do is try to factor this, and hint, it's got 4 terms to it, so that should lend itself to a particular type of factoring that we've used repeatedly in this course. Take a few minutes to do that. All right, well, we're going to factor this thing by grouping. Here we go. So the first thing I'm going to do is I'm going to write it as x cubed minus 5x squared plus negative 9x plus 45. All right, in the first set, I'm going to factor an x squared out. That's going to leave me with x minus 5. Then I'm going to factor a 9 out of the other one. Also leaves me with x minus 5. Continuing to factor, I'm going to run out of room, but we'll give it our best shot. X minus 5 times x squared minus 9. And I think I can fit it in. X minus 5 times x plus 3 times x minus 3. Whew, just made it. There we go. So written in completely factored form, that cubic, right, can be then written as x minus 5 times x plus 3 times x minus 3. Let's take a look at letter B. State the values of the polynomial's zeros. Well, that you should really be able to do by just looking at this, what we call in math, state them by inspection. Why don't you go ahead and do that? All right, well, remember the zero product law says any value of x that makes any one of these 3 factors equal to 0 will make the entire function equal to 0. To make x minus 5 equal 0, we would have x equals 5. To make x plus 3 equal 0, we would have x equals negative 3. And to make x minus 3 equal 0, we would have x equals positive 3. Maybe make that look a little more like a 3. There we go. All right, so it's got 3 zeros, and remember, for a polynomial, the maximum number of zeros it can have is equal to the degree of the polynomial, the maximum number of zeros. So here we have 3 zeros for this polynomial. Let's take a look at letter C. Use your calculator to help draw a sketch of the function using the indicated window. Accurately plot the function's zeros. Awesome. Well, I'm not going to break out the calculator yet. What I'd like you to do is take your calculator, put the function in, the original function in, right? Our x window from negative 5 to 10, that's going to fit all those zeros in. My y window from negative 60 all the way up to 80, because this cubic function can get quite large. So get a nice sketch of that and make sure you accurately plot the negative 3, the 3, and the 5. All right, well, here we go, the magic of the wall, there they are. Our zeros here, I plotted in red at negative 3, 3, and 5, right? Ends pointing in opposite directions, long run behavior down this way, up that way, given the leading coefficients equal to 1. There we have it, right? And again, we can see how the factors of our polynomial reveal structure within the polynomial, specifically its x-intercepts or zeros. All right, let's keep going. Now we're going to talk about something called double zeros. This is sort of cool. Sometimes a factor of a polynomial will occur more than once. If it occurs twice, it leads to an interesting feature on the graph of the polynomial. Let's take a look at that in exercise number 2. A cubic function is given in partially factored form by g of x equals x plus 4 times x squared minus 4x plus 4. Letter A, write the cubic in completely factored form. All right, so in other words, what I'm asking you to do, I don't want you to multiply it out. That's the opposite of what I want. I want you to just factor that quadratic, right? But get down the entire cubic in factored form right there. Pause the video now and go ahead and do that. All right, well, we already know that I've got my x plus 4. And then I just really have to look at this, x squared minus 4x plus 4, two numbers that have a product of positive 4 and a sum of negative 4 would be x minus 2 and x minus 2. So there is g of x in its fully factored form. Now, you might notice, right, that two of the factors are identical, x minus 2 and x minus 2. Nothing wrong with that. Take a look at letter B. What are the zeros of this function? Well, just like before, right? X plus 4 will have a 0 of x equals negative 4. X minus 2 will have a 0 of x equals 2. Now, there's no reason that we have to write down the other one as well, okay? You know, the zeros are x equals negative 4 and x equals 2. Those are the two values of x that will make g of x equal to 0. All right, letter C. Use your calculator to help draw a sketch of the function using the indicated window. So similar to before. Accurately plot the function's zeros. Now remember, right, what this is telling us, what the algebra is telling us, is that the function will touch the x-axis when x is equal to negative 4 and when x is equal to 2. And nowhere else. Nowhere else. There is no third zero, even though this is a cubic polynomial. Pause the video now and get that accurate sketch. All right, so it ends up looking like this. Now, here's that 0 at x equals negative 4, and here's that 0 at x equals 2, right? Let's talk about that 0 at x equals 2 a little bit. Letter D. How does the double 0, also known as a double root, differ on the graph from a normal 0? All right, so I would call the x equals negative 4, right? I would call this a, quote, normal 0. There might be some math teachers that don't love that term. And this I'm going to call a double 0. All right, because, right, you could think of it as, oh, hey, I had a 0 at x equals 2 and another 0 at x equals 2. They're the same 0, right? But how does it differ? Well, at x equals negative 4, right, what happens is that the graph actually passes through the x-axis, and at our double 0, it simply comes down, touches the x-axis, and then goes back up. And of course, it makes sense that it just touches and goes back up, because were it to go below the x-axis and then come back up, which it must, because it's a cubic, right? If it were to go below the x-axis and come back up, it would have 3 distinct zeros, but it doesn't, right? So the normal 0, at the normal 0, the graph passes through the x-axis. All right. At the double 0, it is tangent to the x-axis. Now you saw the word tangent, the red pen strikes again. You saw the word tangent a lot in geometry, right? When we had a circle, right, where we had a tangent line that just touched the circle, right? A tangent, all right? When a graph is tangent to the x-axis, it comes down and touches the x-axis, but then goes right back up without passing through it. Now, what's probably pretty obvious is that the only way you could be tangent to the x-axis is if you also had a turning point there, right? Which is exactly what's happening. It's also what happens to y equals x squared, right? Y equals x squared has a double 0 at the origin, right? It comes down, hits the origin, and then goes back up. So it's not the first time that we've seen this. So let's talk about what's called the multiplicity of zeros. If a real zero occurs an even number of times, so it's not just double, if it happened 2 times, 4 times, 6 times, whatever. If a zero occurs an even number of times in a polynomial, then the graph of the polynomial will be tangent to the x-axis at this location. If the real zero occurs an odd number of times, the polynomial will cross the x-axis at this zero. So it's kind of cool. Now, of course, we could talk about zeros, we could talk about factors, right? So the factors are what are giving us the zeros, all right? So we could say if a factor shows up an even number of times, then the zero that comes from that factor, right, will be a tangent zero. And if it shows up an odd number of times, it'll actually go through the graph. So let's take a look in exercise number 3 at a quartic function in x to the 4th. A quartic function is given in partially factored form by f of x equals x squared minus 9 times x squared minus 9x plus 18. Letter A, write the function in completely factored form. Okay, well, pause the video now and write this function in completely factored form. Obviously, you'll factor that one using one technique, and you'll factor that portion using a different technique. Pause the video now and go ahead and do that. All right, here we go. Well, that x squared minus 9, right, that can be factored as x minus 3 times x plus 3. The trinomial, we would have to find two numbers that have a product of positive 18 and a sum of negative 9. Those two numbers would be negative 3 and negative 6. So that trinomial factors as x minus 3 times x minus 6. Letter B. Based on A, what are the zeros of the function? All right, this is pretty easy. Pause the video now. Tell me what the zeros of that function are. Well, this one would have a 0 of 3, this one would have a 0 of negative 3, this one would have a 0 of 3 again, and this one would have a 0 of 6. So we're just going to list zeros once, but we have 3, negative 3, and 6. So here's a quartic, an x to the 4th, that has 3 zeros. Letter C. Will the graph of f of x be tangent to the x-axis at any of the zeros from B? If so, which? All right, well, we just talked about this in exercise number 2. Pause the video now and tell me if any one of these 3 zeros will end up being a situation where the graph is tangent to the x-axis. You bet. It'll be tangent to the x-axis at x equals 3 because that is a double zero, right? So, yes, at x equals 3 because it is a double zero. Awesome. Now letter D. Sketch a graph of f of x using the window indicated. Verify your answer to C. All right, well, take out your calculator, throw in the original function, use this window, get a sketch, and make sure to nail down that double zero at x equals 3. All right, cool. Well, the magic of the board, here it comes. There it is, right? And here is that 0 at x equals negative 3. There's that 0 at x equals positive 6. And there is that double zero at x equals 3. Isn't that cool? Right? Now, obviously, quartics can have up to 4 real zeros. This quartic only has 3 of them because one of them got doubled up. All right. So let's keep going. Let's talk about the factored form of a polynomial. If we know the zeros of a polynomial, we can create its equation in its factored form using the following. Let's talk about the factored form of a polynomial. If the set z1, z2, z3, etc., all the way to zn represent the zeros of a polynomial, with some perhaps repeating, then the polynomial can be written as f of x equals a times x minus z1 times x minus z2 dot dot dot, all the way down to x minus zn, where a is the leading coefficient of the polynomial, right? That leading coefficient, that coefficient of the highest term. So let's see how this plays out in exercise number 4. A cubic polynomial is shown graphed with zeros at x equals negative 6 and x equals 2. The cubic polynomial passes through the point negative 4, 216. Letter A. Write the polynomial in its factored form, leaving the value of the leading coefficient a undetermined. All right, so this is critical, right? Here we have a single zero at x equals negative 6, and this, because it's tangent, must be a double zero at x equals 2. All right, what that now tells me is that in its factored form, this must look as follows. A times x plus 6 times x minus, whoops, let's try that again, times x minus 2 times x minus 2. All right, the x minus 2 has to show up twice for us to have a double zero there. Side note, if the x minus 2 didn't show up twice, if it just showed up once, this wouldn't be a cubic. It would only be a quadratic. It would only have an x squared in it. Now, what we don't know yet is the value of a. So let's talk about how we figure that out, ironically, in letter B. Use the point negative 4, 216 to find the value of a. Then write the polynomial in its factored form and check using your calculator. Awesome. So this is really cool. You know, given the zeros, right, this is the best we can do. But if we know one other point, we can then nail down what the leading coefficient is. And here's how we're going to do it. We're going to take 216 and we're going to substitute it in for y. And we're going to take negative 4 and we're going to substitute it in for x. And the only thing that will be left will be the a. So let's do that. 216 is a times negative 4 plus 6 times negative 4 minus 2 times negative 4 minus 2. All right, let's keep going. Now remember, everything on this side is multiplication. So that's going to be, I mean, like all these parentheses are multiplying each other. Negative 4 plus 6 is 2. Negative 4 minus 2 is negative 6. And negative 4 minus 2 is negative 6. Now if you need to, obviously at any point use your calculator on this. Negative 6 times negative 6 is 36 times 2 is 72. All right. And so now what I can do is I can solve for this by basically saying, well, I've got 72a is equal to 216. Divide both sides by 72. That's maybe where we want our calculator. And we find that a is equal to 3. Now that's just simply the leading coefficient. The actual now equation of my polynomial will be 3 times x plus 6 times x minus 2 times x minus 2, or y equals 3 times x plus 6 times x minus 2 squared. Either one of those is absolutely fine. Okay, so point is, right, by knowing the zeros, we're able to write the factored form of the polynomial all the way out, except we don't know the leading coefficient. But if we have one other point, and it can't be a zero, it's got to be some other non-zero point, then we can substitute, oops, wow, that is just not what I wanted to have happen. We can substitute that point, in this case negative 4 to 16, into this general form of the polynomial, factored form of the polynomial, and the only thing that will be left will be a, right? Easily solved, in this case, a is equal to 3, and now we've got that formula. And now let's take a look at the graph. All right, let's make sure that we have it right. So here we go. Bring our calculator out. We have 3 times x plus 6 times x minus 2 times, I'll put it just all in its glory, x minus 2. All right, maybe I'll try to actually get the window to look the same. That window goes from -10 to 10, but the y window is much larger. -100 to, come on, 300. And there's my graph. Right? The lovely thing is it's easy to verify that we have the right equation by simply putting it in. Now, one of the keys is, we can definitely see that our zeros are right, a 0 at 6 and a double 0 at 2. Sorry, one of my zeros at -6, a double 0 at 2. The thing that's a little bit harder to tell is the fact that we've got the point -4, 216. For that, we would have to literally, ask our function, what is f of -4 to verify that it's 216. All right, let's try one more problem like that. And let me just forward it. Here we go. Exercise number 5. Write the equation of a quartic polynomial in factored form that has zeros of -5, -3, 1, and 6, and which passes through the point 4, 189. All right, so notice none of the zeros are doubled. Not that that particularly matters, right? None of the zeros are doubled. So what I'd like you to do is try this problem based on what we did in the last problem. All right, so the first thing I'm going to do is I'm going to write down its generic form with the leading coefficient unknown. Now, because we have a 0 of -5, we must have a factor of x plus 5. Because we have a 0 of -3, we must have a factor of x plus 3. A 0 of +1 means a factor of x minus 1. And a 0 of +6 means a factor of x minus 6. So one way or another, my polynomial has that general form. I just don't know what the value of a is yet. But that should be pretty easy based on my zeros. Now, to figure out the value of a, I'm going to put 189 in for y, and I'm going to put 4 in for x. So let's do it. 189 in for y, 4 in for x. Now, how much arithmetic you do on this before you bring the calculator out is kind of up to you. You could literally put this expression into your calculator to figure out what is multiplying a. Or if you wanted to, you could go sort of a further step, and you could say I've got a times 9 times 7 times 3 times -2, right? You could do all of that, all right? At some point in time, you're likely to chuck this thing into your calculator and find that all of this ends up being equal to -378. So we would have -378 times a is equal to 189. Divide both sides by -378. And again, if you're kind of like, well, I don't know what that is, awesome. I might not know what that is either, by just sort of looking at it. So maybe I do 189 divided by -378. It won't always work out nicely, but in this case it does. My a value is -1/2, right? Giving me both sort of a vertical compression and a reflection across the x-axis. Not that that matters so much here, but, right, I get a equals -1/2. And now the factored form of my polynomial I get by just putting that value back in here. Y equals -1/2 times x plus 5 times x plus 3 times x minus 1 times x minus 6. And again, I want to emphasize this is the factored form of the polynomial, not the polynomial written in standard form. You can imagine, right, to write the polynomial in standard form, you'd have to multiply all 4 of those factors out, then distribute a -1/2 through that final answer. But we like the factored form because we can see all of the zeros in it. All right, let's wrap this up. So today, we kind of reinforced the connection between the zeros of a polynomial, right, and its factors. We saw how we could take a polynomial written in standard form or written in partially factored form and factor it completely so that we could identify the zeros, especially if they're integers or rational numbers. Much more difficult if the zeros are either irrational numbers or, even worse than that, imaginary numbers. All right. Mostly in these kind of problems, we will deal with situations where the zeros are either integers, primarily, or rational numbers. We also saw, right, the idea that if a zero shows up more than once, most often at this level twice, to give us something called a double zero, then the graph of the polynomial will be tangent to the x-axis in that case. It will also be tangent to the x-axis anytime a zero shows up an even number of times, and will pass through the x-axis anytime the zero shows up an odd number of times. Most often once, right? Don't get me wrong, you could have a situation where a zero shows up 3 times and that would also pass through the x-axis. Finally, we used all of this to write equations of polynomials if we knew all of their zeros and we knew one other point on the polynomial. In that case, we first write the polynomial in its factored form, leaving the leading coefficient unknown, and then we use that extra point to figure out the value of that leading coefficient. All right, well, we'll work with polynomials more as we move throughout this unit. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.